Okay, this morning we're talking about sets, and I'm going to do this a little bit differently. I'm not going to put in all the requests to pause. I'm just going to go through this fairly quickly. A few places I will stop and say pause to get you to really look carefully at something, but what you ought to do is take this as kind of a lecture and then go back through these notes, and you can try to solve all the problems ahead of looking at the next slide and see if you remember everything that I said, okay? So sets, lists, and tuples, we're going to start out by contrasting those three things. And if you read the DataCamp tutorial on sets, contrasting sets, lists, and tuples, unlike lists or tuples, sets cannot have multiple occurrence of the same element and store unordered values. So I want you to create three things: a set, a list, and a tuple, all of which contain cat, dog, and parrot, and then print the type of each. So here's the list, cat, dog, and parrot. There's the tuple, cat, dog, and parrot. There's the set, cat, dog, and parrot. And you notice that the difference is that the list is enclosed in square brackets, the tuple is enclosed in parentheses, and the set is enclosed in curlies. And you see that they print out, when you print out the type, this is a list, this is a tuple, and this is a set. Okay? So attempt to obtain the first value of each collection. How does Python respond? Well, if you print a list bracket 0, you get cat. If you print a tuple bracket 0, you get cat. And this seems to be kind of misplaced. If you print a set bracket 0, it fails with type error. Set object is not subscriptable. That is, there's never an order in sets. Things are just simply in sets or not in sets, but they're not in any particular position in a set. You can't get something out of a set by using a numerical index. Write for loops to iterate over and print the contents of these collections. Observations? Well, let's do that. Take a list. For I in a list, print I, cat, dog, parrot. A tuple. For I in a tuple, print I, cat, dog, parrot. For I in a set, print I, dog, parrot, cat. So what do you observe? Again, this reinforces the idea that in sets, there is no order. Things are simply there or not there, but the order in which they present is totally arbitrary. So create B-list, B-tuple, and B-set. They have the same items as the A variance, but the cat appears last instead of first. So it's dog, parrot, cat, dog, parrot, cat, dog, parrot, cat, and you got a list, a tuple, and a set. Now let's see what we can do with these. Test the A and B variance for equality. And what do you observe? Well, you ask, is A list equal to B list? No, it's not, because they have to be in the same order. Is A tuple equal to B tuple? No, they're not, because tuples also have to be in the same order. But if you ask, is A set equal to B set, it is true, because in sets it doesn't really matter. The order is not important. All that matters is that the same things are in the set. Okay, so now the C variance. To each of the collection definitions, add another dog as a fourth entry. Cat, dog, parrot, dog, cat, dog, parrot, dog, cat, dog, parrot, dog. So there are your new C variants. They've got a second dog. Exercise. Print each of these and observe the difference. If you print the list, you get cat, dog, parrot, dog. If you print the tuple, you get cat, dog, parrot, dog. If you print the set, you get dog, parrot, cat. Dog is either in the set or it's not in the set. It doesn't matter how many times you list it in the set. It is either there or it is not there. And if you ask to see the set, it will not repeat that dog is there twice because, hey, you don't need to be told twice that it's there. It's just there or it's not there. Try the len function on the C variance. And if you print the length of C list, you get 4. If you print the length of C tuple, you get 4. And if you print the length of C set, you get 3, because there are only 3 things: cat, dog, and parrot. Sets and dictionaries. You notice that dictionaries are also included within curlies. And what's the difference between a set and a dictionary? Well, the items in the dictionary are two things separated by a colon. And in a set, you simply have the list of three things, and there is no colon separating the parts of the individual items. So if you print the dictionary, you have 2 dogs, 1 cat, and no parrots. And if you print the set, you get Fido, Rover, and Felix. So 2 curlies with nothing included, well, what would that be? It's got to be an empty dictionary because that's already been claimed. An empty set, how do you create an empty set? It's just simply the word set followed by parentheses, and that's the way an empty set is created for the beginning of an accumulation pattern. Okay, so I'm going to add a Python to the dictionary and the set, and the Python's name is Cool Guy. So the dictionary, I just take the key Python and give it the value 1, and the key Python was already there, but it didn't really need to be. And to the set, I add the name Cool Guy. And if I print the dictionary, this is what I get: 2 dogs, 1 cat, no parrots, 1 python. And if I print the set, I get Fido, Rover, Felix, and Cool Guy. I had to give the second dog a name. Sets are mutable. Okay. The cat died, so we want to update the set and dictionary. We update the dictionary by saying that the count of cats is now 0. And in the case of the set, the method that takes something out of a set safely is discard. So I discard Felix from the set of pets. Now I print the dictionary. I still got 2 dogs, no cats, no parrots, 1 python. And if I print the set, well, Felix is gone. I've just got Fido, Rover, and Cool Guy. That would be an interesting household. Note that the set doesn't print in alphabetical order. You can use the sorted function to solve this problem, create sorted underscore pets. You might ask, what's the type of this new object? If you apply the sorted function to a set, what do you get? Sorted pets is sorted of pets underscore set. And the type of sorted underscore pets is a list. Has to be a list because the set has no order. And if I print sorted pets, I get Cool Guy, Fido, and Rover in the proper order. Python comes first, of course. 2 functions. The function set turns a list into a set. A set is unduplicated. The function list turns a set into a list. You could use these facts to write a function, undupe, which converts a list with duplications into an unduplicated list. And I ask you to test it on 1, 1, 2, 3, 4, 4, 5, 1, 2, 6. And you notice I've duplicated the 2s, I've duplicated the 4s, and I've triplicated the 1s, okay? So how does undupe work? Undupe of list, return the list of the set of the list. So I print undupe of that list, and I get 1, 2, 3, 4, 5, 6. And yeah, it took out all of the extras. Because when you turn it into a set, the extras disappeared, then you turned it back into a list, and now you have a list which has been unduplicated. Provided, of course, sets can only have immutable members. So you couldn't do this with a very complicated list. Range to set. Does the set function work on range objects? Well, let's see. I create a list. I100, integers 100, is set of the range of 1, 101. And of course, this range of 1, 101 would produce 1 up to 1 before 101, which would be 100. And if I print I100, what I get is, and it runs off the side of the page, but you've got the numbers between 1 and 100. And then if I print the length of 100, I100, I get 100. And if I print the type of I100, what I get is a set. So Python somewhat awkwardly displays the result as a set of a list. So let's use this set as our universe. Any real serious mathematical discussion involving a bunch of sets requires that you first establish a universe, that is, the set of all possible elements which will appear in this discussion. So how many subsets does a set of length 100 or have? How many subsets do you have if you have two elements? And the answer is the first element could be either there or not. The second element could be either there or not. And that would give you 4 possibilities. And then if there were 3, well, to the 4 possibilities, each one would have an option where the third element is there or not, and the fourth element, the third element is there or not. So that would give you 2 cubed. And obviously, if you have n elements, the number of possible subsets is 2 to the nth. So 2 to the 100th, which is, gosh, that's a big number. And I don't want to try to write it out. Okay, so I'm going to rename I100 as the universe. So the universe is I100. And we're going to create some subsets. I'll start with evens, the subset of even numbers. And we know how to do that. First, you make evens an empty set. Then, for every n in the universe, if that value of n is evenly divisible by 2, you add it to the set evens, and after you're done, you've got the set evens. And then we print evens, and again it runs off the end of the page. We won't do this in CoCalc. That's a pretty standard pattern. you start off by getting something that has nothing. An empty set in this case, and then you add to it as you iterate through the possibilities. There's that pattern has sort of an abbreviation, an equivalent form, and I'll call it evens under comprehension. This is called a comprehension. X, for x in universe, if the remainder upon dividing x by 2 is 0. So the way this works, it goes through every element in the universe, and then it says, well, if that value of x is evenly divisible by 2, then you will accept that value of x. And this produces a set because it is enclosed in curlies. Okay, very, very brief alternative to this sequence of things up above, which by now is kind of becoming second nature to you, but this is a much shorter, quicker way to do this. And I call that thing evens underscore comprehension. So I ask, is evens underscore comprehension, is that the same as evens? True. So that notation x for x in seems redundant, but it has a purpose. And the reason is that you could do something different here. You wouldn't have to take just x. You could take something based on x. And here's an example of doing that. If I took the squared evens, what I would want is, I'll again run through x in the universe and ask if that particular value of x is evenly divisible by 2. And if that's true, then what I put in my set is not x itself, but the square of x. And that's why this is kind of an overly simple example where it seems to be redundant, but it's not. Okay? Create the set of odds using comprehension. Yeah, that's when you probably want to stop for a minute and copy the code from the previous exercise and see if you can create the odds. But it's pretty easy to do. So the code is almost the same. The odds is n for n in universe if the remainder upon dividing n by 2 is not 0. That would identify an odd number. And then you print the odds and you get 1, 3, 5, 7. Something important to notice here, I used x before, I used n this time. Does it make any difference? Well, this thing right here, n, they all three have to be the same for this to work, but it could be any legitimate variable name. And the resulting set that you get does not have anything to do with a particular variable name that you use to create it. It just disappears. Create the set half-1, consisting of every number 50 or less. Hint, put a conditional at the end of the comprehension definition. And this is an option that I didn't show you in the original comprehension definition. But let's look at how that's done. N for n in universe, and then I didn't do anything to this n here. What I did is to add a conditional after the for n in universe if n is less than or equal to 50. And this set here ends at 50. You can see that more easily in GoCalc. Okay, so now I want to create the sets div3, div4, and div5 containing the numbers divisible by 3, 4, and 5 respectively. And this is to give us some exercises on set operations. Okay. Well, div3 is n for n in universe if the remainder upon dividing n by 3 is 0, and the same thing with 4 and 5. And this is pretty obvious. So here we've got the divisors, the things that are evenly divisible by 3, the things that are evenly divisible by 4, and the things that are evenly divisible by 5. And that gives us some subsets of the universe to practice set operations on. Create and print the intersection of div3 and div5. Well, intersection is written as div3 ampersand div5. And another way that you can write it is div3 dot intersection parentheses div5, but I prefer this notation very much. So print div3 and div5, and these are the things which are divisible by both 3 and 5 in the universe that we've settled on. Create and print the union of div3 and div5. And this is div3 vertical bar div5. In some languages, this is the symbol for OR. And union, you'll realize, is really essentially equivalent to OR. So print div3 or div5, and you get 3, 5. This one is there, divisible by 3. This is divisible by 5. This is by 3, by 3. This is divisible by 5. This is divisible by 3. This is divisible by both. Okay. Create and print the set difference of div3 and div5. Well, difference is minus. Div3 minus div5. This is take all the things which are divisible by 3 and not divisible by 5. So all of these things are divisible by 3. None of them are divisible by 5. Okay? Create and print the symmetric difference of div3 and div5. And the symmetric difference, the symbol is caret. Div3 caret div5. Print div 1 of 3 and 5. This is something that is either divisible by 3 or divisible by 5, but not by both. So you realize this is why you lost a 15. It was divisible by 3, it was divisible by 5, and because it's divisible by both, it got excluded. In logic, we had negation or not s, a really primary operator. With sets in, there's also basically complement, a very fundamental concept in sets. But Python doesn't have a natural built-in complement operator because there's no obvious definition of the universe. However, once you have defined the universe, you can implement complement as a function. Okay? And the way you do that, the complement of a set S is the difference between the universe and the set S. That is, all those things which are in the universe but not in S. And it's this problem of having to specify a universe which prevents Python from having a built-in complement operator. But once you've defined the universe, it's easy to do. So I'm asking here, is the complement of the evens equal to the odds? And the answer is yes, that's true. Union distributes over intersection. In general, the theory of Boolean algebra, which is the common name that we give to the algebra of logic and the algebra of sets, it's really kind of the same thing looked at in a different way. And this says that union distributes over intersection. That is, A union with B intersect C is the same thing as A union B intersect A union C. And we're not going to prove it, but I just want to show that this is true for an example using div3, div4, and div5. So the left side will be, and this is the left expression, is div3 or union div4 intersect div5, and the right side is div3 or, union. Union and or are the same thing, so I've mixed them up. Div3 or div4 and div3 or div5, and I ask, is the left side equal to the right side? And yes, you get that that's true. Okay, we've gone through this fairly fast, and what you should do now, having seen the video, is to go back and look through the notes, and as you progress through the notes, try to answer each question before you go on to the next slide. Okay, so that's enough for the theory of sets.